Hello and good morning and good afternoon. Welcome to this second session of the Quantum Nuggets, Quantum Bits and Quantum Mechanics. My name is Giuseppe Cinque, and we will go through in the next hour the key fundamental concept from quantum mechanics that allow us to create this concept of computing using system from quantum mechanics, like they are called quantum bits. If you haven't seen the previous version, I recommend to see the link and follow the link for the previous version, because just as a reminder, in the first version, we looked at what is a quantum computer, how we should think about a quantum computer, especially in terms of quantum processing unit. We have done an hello world circuit with a cloud available quantum computer. And then we have talked in the second part, very importantly, how some algorithms that are that function only on quantum computer are creating some risk for current asymmetric cryptography like RSA, but also how to protect. What are the post-quantum standards that have been proposed that are resistant to quantum attack, and even at the end, how you can today secure your email for a quantum computer attack. Now we are gonna go deeper, and we are gonna get into the rabbit hole, searching for these quantum nuggets, starting from quantum mechanics for then understanding what are the qubits. And I will use some interactive tool that I've developed for this session to demonstrate some concept. In particular, the concept of superposition, the concept of quantum gates, and at the end, the concept of entanglement. That will be the foundational knowledge to then go on the third session around May, where we will go deeper on the aspect of quantum networking and quantum internet. So very excited about that, but let's get started. So first of all, it's important to know that this domain is called quantum science and technologies, and it's about the use of subatomic particle, in particular some special behavior like superposition entanglement that I've already said, to transform not only the computing but also the communication, and very important also the capacity to do a better sensing, so to create a better sensor. But of course, this is a domain where easily you can get to very deep and very complex. So I will use this cute rabbit to show the level of depth. And the rabbit hole level 1, it means that these are the key concepts that are sufficient for broader understanding. Some here and there, I may go to rabbit hole 2, where are deeper concepts that can help a deeper understanding. And then there is rabbit hole 3, where probably are very, can become mind-blowing concept, but are there more for inspiration. And so we can go up and down on this level. But let me start with a story. When I was preparing for this session, it came to me a story of Kepler. And it was about New Year's Eve of 1611. And he was going to an important party, and he realized he didn't have any gift. And he was on Prague on a bridge, and he was snowing. And he was paying attention to a snowflake. And he realized that there is such a beauty inside the snowflake. And he was pondering why this snowflake always have this six-side symmetry. Why not 5? Why not 3? Right? They always have this six-side symmetry. And he decided to write an essay and to make this as a gift for his host. So he created this essay, and of course he started to think that it must be connected with the nature of the water, with something that is intrinsic in the water that makes this possible. And it is true, but he couldn't have the right knowledge, the right information to demonstrate that. because only few hundreds years later, with the work of Cavendish and Lavoisier, we discovered that water is not a fundamental element, but is made by two gas, right? Hydrogen and oxygen. And even so, you cannot understand how this can create six-side symmetry. Because if you know that the molecule of water is two atoms of hydrogen and one of oxygen, you may think that the structure is linear because the hydrogen tends to be positively charged, so this will tend to go far away. And so this will be, what you would expect. But in reality, you find that the molecule of the water has a band. And that's through that band that you start to have this hexagonal symmetry that makes the crystal, the beauty of those crystals. So to understand that, to understand why a molecule of water has that shape, you have to get into the quantum computing and quantum mechanics, understanding. And this understanding came in the beginning of the previous century. With the work of a lot of different scientists. First, Planck found out that to explain a specific phenomenon, he postulated the idea that energy is quantized. So he's not continuous, but he's has some levels. He thought it was a mathematical trick, not really something from the nature. But then Einstein, 5 years later, used that concept to explain the photoelectric phenomenon, how some metal, when irradiated with some frequency, they emit electrons. Thinking about the light as a wave wouldn't explain why you need to a specific color of light to have this phenomenon, but he postulated that the color is connected with the level of energy, and you need a sufficient energy to have this phenomenon happening. But most of all, a lot of study about what is called the spectrometry of hydrogen, right? If you put hydrogen inside a tube and you put some charge, so you excite the hydrogen, you start to see some emission of lights, right, of different color. And these are specific color, and people couldn't understand why this specific color were emitted or absorbed by excited gas. They started to create some rules, right, to calculate, but they didn't have a theory. So it reminds me the status of AI right now. We have a lot of pragmatic rules about scaling law, but we don't have a complete theory or what is intelligent. We don't have the Maxwell equation, let's say, of the intelligence. And so, in particularly, they started to develop different idea of what was inside an atom. In particularly, the experiment that they were doing is something like that, right? The first idea was maybe the atom is like a solar system, right? There is a electric charge inside, an electron that rotates, and when they started to irradiate with photons, depending on the color of the photon, as you can see, I can change the color of the photon here. If it's in the blue or early ultraviolet, it doesn't produce any effect. But as soon as I get to specific line of color, you see that the atom can absorb the photon and change his energy states. But then these excited energy states cannot sustain, so the atom re-emits a photon and goes back to the original state. So this concept of quantization of the energy was playing a role also in the mechanics of the atom system. And so this is the Bohr interpretation of the model. And of course, others propose other interpretation like the wave mechanics, where they said it seems that the particle behave like a standing wave. right? So there are different mode of vibration that are excited, and that will help explain some phenomenon like interference and so on. But all of these were kind of, let's say, piecemeal work. It wasn't until exactly 100 years ago, one guy, an Austrian scientist, took a holiday in the Austrian Alps, Erwin Schrödinger. And during that holiday, he had this incredible moment of creativity. And he put, last week, he published 100 years ago, he published a paper that changed forever, right, our understanding of nature. He published the so-called paper on the Schrödinger equation, an equation that was able to describe this phenomenon. It was complementary of another theory that was developed 1 year before by Heisenberg. And together then with other scientists like Dirac, they were able to put together a framework that has created what we now call the first quantum revolution. The use of this tool to produce an incredible amount of success in science and technology. But as I showed even in the first webinar, this picture, because this is the Congress in Brussels in 1927, where all the scientists, most of these people are Nobel Prize. There was the highest concentration of current or future Nobel Prize. And they really kind of put together to say, okay, this is what we understand about how the physics of the microscopic system work. But two of them, Einstein and Bohr, has been reported that were fighting all the time because Einstein couldn't accept some aspect of this theory that we will see. And since then, he has been always kind of remembered to say, God does not play dice with the universe. He didn't like the stochasticity, the probabilistic nature of the theory, of the quantum mechanic theory coming from the Schrödinger equation. And Dirac was responding, he was responding to him saying, Einstein, stop telling gods what to do. Because he thought that when we observe a rule in the universe, it's not our kind of goal to understand why that rule is there, but just to use that rule to predict things and to make more science, more technology. And this approach was also has been known as a shut up and calculate. So don't ask why things are so weird, but just use the tool to the power of the tool to predict and to build and to make more science and engineering. And we have done a lot with the Schrödinger equation, with that understanding of the wave function. That's what has brought us the semiconductor. That's what has brought us the all laser and fiber optics, the medical application like magnetic resonance, or even the atomic clock. And although it's a probabilistic model, it's extremely accurate. So, for example, in the atomic clock, the more recent research on atomic clock, we can build atomic clock that have precision. They will not miss 1 second in the age of the universe. So that's the kind of precision, right? They can keep the time. If started from the beginning of the Big Bang until today, they wouldn't have missed 1 second. And think about, just to have an idea, what is the age of the universe, that is like roughly 50 billion years. One way to visualize this number is to, sometimes people call it the calendar universe time. What does it mean? Imagine that the 50 billion years, it's 1 year. So we compress the 50 billion years, that is the age of the universe, of 14 point something, in 1 year. So for most of the time, the Earth even doesn't exist. It will start to show, the sun and the galaxy will start to show up in September, right, in the calendar. And you know when all the human history will start to show up? If we map 15 billion years in 1 year, all human history will be the last 10 seconds of the last day of the 31st December. So that's kind of the proportion, right? So imagine that in that huge amount of time, this atomic clock that have been built using the rules of quantum mechanics will be able to keep the time. So they are is an extremely precise theory. But, Einstein was perplexed. And what he was saying is, I'm not saying that is not correct. I'm saying it's not complete.
I am not saying that quantum mechanics is not valid theory. I am saying that is not complete.
And what does it mean that is not complete? He was thinking that it was a good predictor, but there were some kind of hidden variable. There was still something that was missing in the model, and we eventually would have discovered that. And this culminated in a paper that he wrote about 7-8 years later of the Congress in 1935 with other two researcher scientists. In fact, the paper is called Einstein-Podolsky-Rosen paper. An interesting story, one of the researchers sent the paper to the newspaper before publishing. And so all the newspaper published this news that Einstein was attacking quantum theory, and made Einstein very disappointed that he didn't speak anymore with his colleague because of this. And if we look at his paper, at the research production, it's interesting to notice that the most cited paper of Einstein is the paper regarding this problem. Can quantum mechanics description of physical reality be considered complete? So it's not the special relativity, it's not the general relativity, it's not even the photoelectric theory that earned him the Nobel Prize, but is this paper, such important paper. Why? Because in this paper, he was, with the intent to show a paradox, he was showing the behavior of nature of two particles that are far away, and showing how the property of this particle, even if extremely far away, they will still be correlated. That is called the entanglement. So he was using this demonstration as a paradox to say this cannot be true, right? Things cannot have this spooky engagement at the distance. There must be some hidden variable, something that we have missed, and we need to work on that. And but in reality, what we will see, it seems instead that this theory is correct. And it's also one of the reasons why the second quantum revolution, the quantum system that we are building now, they leverage this incredible, unintuitive, mind-blowing property of entanglement. Very, very high level, what does an entanglement means? As I said, let's think for a moment of a system. A mechanical system is totally an analogy, right? Two gears that rotates. We know that if one rotates in one way, the other needs to rotate on the other way, right? Because that's the mechanics. But what if we put these two gears that have interact for a moment far away, and we cannot see because they are in a box, but then we open the box and we observe? What the entanglement says that if we measure the status of one gear and is rotating on one verse, for sure the rotation of the other gears must be on the other side. Even if you're not touching, if there is no connection, no signal that goes from one side to another, there is a pure statistical correlation of this phenomenon, no matter how far away they are. So that's kind of what Einstein couldn't accept. So again, how does this apply to quantum computer? Feynman was the first to realize that the Schrödinger equation is extremely powerful to predict very simple system, like an electron in an idealized hydrogen atom. Even college student can calculate. But when you start to have a more complex system, for example, atoms with more electrons or more simple molecule, the number of particles drives the numbers of parameters of the equation exponentially complexly. So the complexity of solving the equation, even with the numerical methods, grows exponentially. And he said, okay, but nature should how nature is able to compute? There must be something in nature that is able to treat those untreatable problems. And so in some senses, he thought, oh, if we have this complexity in nature, maybe we can use nature, we can use quantum mechanics to compute quantum mechanic problems. And this is not a new idea, right? We have seen many times that computing is in some sense could be mechanics. So this is Gaudí, that when he was designing the architecture for the Sagrada Familia in Barcelona, to understand the tension, right, of the different structure, he was creating a model upside down with weights and string. And so having the nature, the gravity, pull the strings and the weight. And because the kind of tension or the pressure are one of the opposite of the other, if you take a picture of that structure and you put it upside down, you have the ideal structure, a self-sustaining structure of a cathedral. So he was, again, using this case classical mechanic to compute specific structural mechanic for his architecture. So really genius. And that's why we get to today. So last year, the Nobel Prize for Physics has been assigned to these three scientists, Clark, Deverett, and Martinez. And if you have watched the WEF videos, Martinez has been doing a lot of lecture and panel about quantum mechanics. And why we have the Nobel Prize on this? Because of the work they have done to discover quantum phenomenon at, let's say, macroscopic level. What does it mean? They have created circuits based on one phenomenon that was discovered by another scientist, another Nobel Prize called Brian Josephson, who had this idea when he was 22 years old of essentially using superconductor with a junction, and to show that you can build a circuit, so something that is microscopic, let's say, that manifests quantum mechanic properties. That's fantastic, because now we know how to scale circuits. We know how to create highly integrated circuits. And so he started kind of creating this kind of tools and system to cool down, that then has paved the way for creating the quantum qubit based on superconductive technologies. But superconductive technologies are not the only technology used for quantum bits. There are many different ways to create quantum bits. There are systems that use trapped ions in electrical trap, for example. Or we can use photons that, of course, manifest quantum phenomenon. And more recently has gained a lot of popularity the use of neutral atoms. So pure simple atoms that are trapped together using lasers and electromagnetic chamber. And this is becoming an incredible, powerful technology, because it's amazing the level of control of individual atoms. Here you see, for example, 3D organization of individual atoms that have been demonstrated. Or here is the funny Mario Bros, made of qubits. So there are individual atoms that can be moved around using this concept of optical tweezer. So using a laser as a kind of small tweezer to move atoms around and then to control the excitement state of this individual atom to perform calculation. So it's amazing the level of engineering. Like in the superconductive, we have microkelvin temperature that is, an order of the magnitude lower than outer space level of temperature. And here we are controlling single atom position. It's really amazing the level of sophistication we have reached with a lot of Nobel Prize that have produced the science and the technology. So with this idea of the neutral atom trapped, I kind of got an inspiration for a mental model for a qubit. So how can we understand a qubit? But before going there, let's for a moment step back and think, reflect for a moment, what is a bit? What is a classical bit? So the idea of bit was kind of socialized and made public by the work of Claude Shannon, another incredible genius, and has a basic unit of information. So the information required to know if something is in one of two possible states. Oh, the classical example is a two-state circuit, a circuit that can be closed and with electric current flowing, or open without electric current flowing. And we can describe this as the bit associated with this circuit is 1 if it's closed, or is 0 if it's open. And of course, we have used several technology from switch relay to vacuum tube to transistor to integrated circuits to shrink down and create incredible amount, hundreds, thousands, millions, billions, right? 100 billions of micro switch, micro bits, right? For our computer. But the key concept is that it's a two-state system that we can control. And just a little bit of notation that will help us when we switch to qubit. So very often we represent bits as an inside square, right? Normally we represent strings of maybe 32 bits for an IP address, and we can put 0, 1, 1, 0, 0, right? We represent this squared sequence. We could represent also as a graphical visualization, maybe with 2 dots on a line. The one dot represents the 0, another dot represents the 1. This could be another graphical representation. One mathematical trick that, again, it's nice to have. We could even represent a bit using this convention. Just a food for thought. What is the status of bit? Is a combination of a coefficient multiplied 0 plus b multiplied 1 under some condition that a or b can be only be 0 or 1, and the sum of a plus b must be 1. If you think for a moment, this will represent all the possible state, because if it's 0, 1, if 1 is 0, the other should be 1, and vice versa. So you will have only these two states. So this is a little bit of a mathematical trick that is not so useful for binary classical bit, but it will be very useful for qubits. In the case of digital bits, that's kind of the condition. What about quantum bit? Quantum bit are systems that are based on quantum mechanics, right? So instead of representing them as a square, there is this notation. It's a notation that is called ket, right? From bracket is the second part of a bracket is a ket. So it's this vertical bar, usually phi of psi, Greek letter are used, and then this triangle. And so this qubit can be 0, can be 1, or can be what is called in a superposition of the possible measurement outcome. So what is this superposition? Is exactly this. Is the multiplication of a coefficient A times the status 0 plus a coefficient B times the status 1. But this time are different, the condition. A and B can be any number, any real number, even more. They can be even complex numbers, right, with imaginary part and so on. So they can be whatever. The only other condition is normalization. The square of the first plus the square of the second must be equal to 1. Why? Because these coefficients we will see are associated with probability. And this condition assures that these numbers look like probabilities. So this is just a notation, but this will start to kind of become more and more familiar. Let's try to create a mental image now, and we will get back to the notation. So as I said, if we want to understand quantum bit, we have to think about a system that has two states that will represent 1 or 0. You can think, for example, two energy level inside an atom, or you can think about the spin of an electron, or you can think about the polarization of a photon. Anyway, it's not important. It's important that we say that is a system that has two possible states, and we call one state as 1 and the other state as a 0. So for our mental image, let's think that we have this coin, and let's imagine for a moment that we make this coin so little, so small, that it becomes a quantum coin. And what I mean is that we are able to suspend this coin with some electromagnetic system. So now the coin is floating and is suspended by this electromagnetic system. If I turn off the electromagnetic system, of course, the coin will fall and I will measure the result. Okay, it's a 0, right? But I also have the possibility to use some laser to rotate the suspension state of this coin. So now the coin is suspended, but is not perfectly parallel to the ground, is a little bit bended. And because of that, I can say, oh, there is a little bit of probability that falling down, I don't get 0, but maybe it falls on the other side, I get 1. And the more, of course, I turn, the more this probability augment. So let's try. Let's measure. Oh, not good. Still 0. So what I can do is maybe put it in this position where is 50-50 and or almost 50-50. Yeah, like this. Let's try now to measure. Yeah, now it's 1. And I can also repeat this experiment n time. For example, let's put 200. So now I'm going to do an experiment where 200 coins will be repeated the experiment 200 times. So for example, let's turn the coin 74%, 26%. This is the a priori probability. If I do the measurement, I have a bunch of coin now. And if I go here and look at how many of them turn out as 1 and how many of them turn out as a 0, I will see here, this is the statistic of the experiment, the 73 have turned out percent as 0 and 27 as 1. That is pretty close to the estimated probability based on the kind of theory, right, of this kind of theoretical quantum coin. So when we see that a coin is in this strange state where I cannot tell for sure if it will be 0 or be 1, because let me say something different. I can, for example, turn the coin on the one side right? Now is suspended, is full on the one side. I know for sure that if I measure, I will have 100% 1, right? Because they are really parallel. So when I have this status where it's not sure a priori, right, what is the probability, that's where we say that the status of this system is in a superposition. There is a coefficient that multiply the 0, and there is another coefficient, in this case, that multiply 1. And to compute the probability, what I have to do is to take the first coefficient, square it, and that will give me the probability of having 0. Take the second, do the norm and square it, and that will be the probability of getting the other outcome. So that's exactly what a qubit status does. The only difference is that usually in the quantum books, in quantum simulator and quantum system, you don't see a coin. You see an abstract representation of a vector over a sphere. You remember there was that condition that a squared plus b squared should be equal to 1. X squared, something squared plus something squared equal to 1 reminds the idea of a sphere. In fact, these points, the points that are that represent the different possible states of a qubit, are all on the surface of a sphere. And I can, for example, put the status of this qubit in this kind of in between from North Pole and South Pole. And when I measure, that's where I will get the outcome possible, right? I can have 0 or 1 as an outcome. So this is exactly the same I was having with the coins. If I go back and reset, if I put the coin like orthogonal to the floor, it's equivalent to put this abstract mathematical system in this equator direction. And if I do the measurement, in this case, I've got 1. But if I repeat, because the probability is 50-50, when it's like this, let's do another measurement. Again, 1. I'll try yet another time, because it should be coming also 0. As you can see, I've had this time the level 0. So what is important? So the qubit is a system, as I said, that can be in base state, like 0 state or 1 state. In this case, when the North Pole represents the 0 state, South Pole represent the 1 state, or could be in intermediate position or superposition of 1 and 0. In this case, for example, is in a superposition. And you can see the representation, the notation, the so-called ket notation. In this case is 1 over square root of 2, 0 minus 1 of square root of 2 times 1. Okay, that's another representation for the qubit. Okay, let me for a moment go back on the classical bit, right? I was saying, okay, for the classical bit, it could be open or closed. I may have a simple graphical representation. In this case, it's not a sphere, are just 2 points. The digital bit is only either 0 or 1. There is no much more that I can do. I said I can represent this mathematically, but it's more like a trick because it's never in a superposition, because it's always one of the two coefficient is always 0. So it's not really, I cannot put a classical bit in a superposition that is between 0 and 1, right? But I can do other things. I can apply logics. So for example, if I have 2 bits at 1 and I have a gate AND, I know that the AND logic of 2 bit at 1 is 1. If one of the 2 bit is 0, of course, the AND logic is 0. I have the OR instead has a different logic. Either one is 1 or both, it gives me 1. Interesting operator are, for example, the NOT. The NOT is a 1 bit operator. If the bit is 0, it gives me 1. If the bit is 1, it gives me 0. Another one that is not so famous in classical circuits, but is important for qubits, is the CNOT, is the controlled NOT. It is acting as a NOT on the first line, so bit 1 becomes 0, if the control signal is on. So if the first bit is on, this acts as a NOT. If it's off, it's just an identity. So 0, it's 0, 1 becomes 1. If this is active, it becomes an inverter, right? So this is an important operator. So the same ideas of gate operation, it's available also for quantum object. And so, for example, I start my qubit on 0 state. I can see that it's 0 state. Mentally, I can think about my coin floating with 0 on the top. If I apply the operator X, so in quantum computing, X is the NOT operator, you see that has transformed 0 in 1, because now if I measure, I will get 1, right? And there is one special operator that is called Hadamard gate. So this H operator, you can think about half and half, puts the qubit in the perfect superposition of being half 0 and half 1. And it's not correct to say half 0 and half 1. The correct way to say it's in a state that has 50% probability of observing a state 0 and 50% probability of observing the state 1. That's the concept of superposition of states in the qubit. And so I have my circuits where I can apply different operator, and this will drive different probability of finding my qubit in different stages. So we have seen two concepts, the concept of status of the bit versus the status of measurement. In the classical bit, what is the status of the bit? It's also what I observe. There is no ambiguity. In the quantum system, there is an ambiguity because the status, here I'm cheating, I'm observing from mathematical perspective, but what I can really observe is only if I measure. And when I measure, I either see 0 or I either see 1 and never see a superposition. I can compute and track a superposition, but I cannot observe directly the superposition. I can observe it in terms of statistic significance. So if I have prepared my status with maybe here 20% probability of having 1 and 79% of having 0, and I do 200 or 300 measurement, I can see this reflected, right? I can see that the outcomes, that is always 0 and 1, are distributed statistically according to that status. So that status was true. But when I observe an outcome. And that's the peculiar situation of a quantum computing system. And the whole idea of finding quantum algorithm is to use this concept of superposition and the concept of entanglement to drive computation in a sense in a parallel way. So to explore the space of possibility and to hope that because of the algorithm, it converge to the solution I'm looking for. So to steer this orchestration of the dynamics of the qubit toward our solution. And that's what Groove's algorithm and Shore's algorithm do. So we have seen the concept of superposition of possible outcome. We have seen a block representation, that is this abstract sphere. You may think as an abstraction, mathematical abstraction. And we have also introduced some operator like the X, that is the not, the H, that is Hadamard, is very important because puts in a complete 50-50 superposition of 0 and 1. And also we have seen the effect of multiple measurement, how the statistic of the measurement are aligned with the expected probability. And we have seen that that probability can be calculated with the coefficient of the amplitude, the coefficient of the status representation. This is called the Born rules. So this is a quick summary of the qubit. So it's a quantum system that shows quantum mechanics property like superposition, entanglement, interference, can be made with different technology, neutral atoms, ions, photons, superconducting circuits, the one that received the Nobel Prize this year for experiment done in 1985. But it's important to remember that the state of a quantum system evolves with the Schrödinger equation, that is a deterministic equation, even though the prediction is a probabilistic one, but the calculation can be is deterministic. When is the strange moment is where you do the measurement. In fact, the big problem in quantum mechanics is the problem of measurement. Why, when you observe a system, it collapses, right? It gets in one particular status, and this status is associated with the coefficient of the superposition. There is a lot of different interpretation of this open problem. One of which, for example, is the idea that there may exist multiple kind of not parallel universe, but multiple in parallel. This unfolds in multi-universe situation. So why now? Why all of this? If it is 100 years old, the quantum theory and the qubit, we have been starting doing it, since years. Why now there is all this excitement? Why now there is the Nobel Prize? Because what we have seen so far and what we have built so far is called NISQ, Noise Intermediate Scale Quantum Qubits. So we have systems with hundreds of qubits, and these qubits are noisy, as we have seen in the previous session, where we were looking at the various parameters of the qubit. But to get where we want to be, that is a fault-tolerant quantum computer, we need to have error correction. And there is algorithm of quantum error correction that have been theorized for a while. But now they are starting, in 2025, they started move from quantum error correction work in principle to we can run in regime that plausibly will scale. These are quotes from pivotal paper of this the last year. So we scientists and engineers start to see line of sight of, okay, seems that they have all the ingredients. It's now a problem of scaling engineering, right? But the science seems to be getting together, and also the principle and the engineering getting together, so that we can really get accelerated to fault-tolerant quantum computer. But how do we create the entanglement with 2 qubit, right? So I've shown you how to work with 1 bit, but I say that very important for computing, it's also and also for even more for communication, is the entanglement. So to create an entanglement, you have to have a system with two bits, 2 qubits. So I have here a very simple quantum computer simulator. So I have 1 qubit here. This is the circuit representation. So the qubit starts from this 0. This is like music pentagram. So I can add operators. For example, if I add X, now my system transition from 0 to 1. In fact, I can see here the calculation. Here is this tool makes all the calculation. We don't need to get into that, but I see that now the probability of finding this is the joint system is composed of two qubits, right? So the first and the second. Now the probability to find the first in 1 and the second in 0, it's 100% because of how I've created my circuit. If I apply the NOT also on the second qubit, now I have 100% to find my system, if I measure my system, to find my system in 1, 1. Okay, so what if now, instead of I reset this circuit, what if now instead of applying this, I apply Hadamard gate? So as we remember, Hadamard gate is the 50-50, right? Puts the first qubit 50% in 0 state, 50% in 1 state. In fact, now my comprehensive system is 50% 0, 0, 50% 0, 1, 0, right? The first bit can be either 0, 1, 50%. The second, we know, because nothing has been applied, that is 0. Now the tricks happen. If then I take the C0 gate and I apply it actually on the other way around, I apply the C0, taking the control signal from the qubit that is in superposition. So the superposition is the control signal, and this is the NOT. I'm kind of saying, you know, it's 50% controlling, 50% NOT, and so this affects also the other qubit. And that's where now I find myself in these interesting states that is called Bell state, 0011. What does it mean? It means that if I measure the first bit, I immediately know what would be the second bit. Because if the first qubit, right, is 0, the second must be 0, cannot be 1. If the first one is 1, the second should be 1, cannot be 0. They are perfectly correlated. And that's the entanglement state. Of course, there is also anti-correlation. I can have a correlation 0, 1, 1, 0, and those are other Bell states. So that's how you build an entanglement with the two qubits. Why this is important? I was mentioning last time, for example, that Cisco has created a quantum chip that is able to produce 200 million of pairs of photon entangled. So it generates entangled photons that can be sent in pairs. And this is important because then you can use this information to create tamper-proof communication. So you can create a communication link that is mathematically demonstrated that can detect if someone is listening inside the channel. So that has a profound implication for key distribution. In fact, this is the basis for technology of quantum key distribution that allows this distribution of keys with proof that have not been tampered. Of course, there is a lot of engineering effort to be put together because of the distance, etc., but is a totally different concept, right, in security. And that's where, you know, teasing up for the next session about quantum networking. But one point is, what if this entanglement is not really true, right? What if Einstein was right, right? Maybe there are some hidden variable, right? This quantum phenomenon maybe looks like a spooky action at distance, but it's not really true, right? That's where a lot of experiments have been done, but I think one of the most fascinating that I've seen is the one that is produced in this documentary. I put the link here from that you can find on YouTube, where in the Canary Island, they use different observatory to do the Bell experiment. So the Bell experiment essentially is sending couple of entanglement particle and doing some interesting measurement at the two sides to see the correlation. And the idea is that if mathematically, if there is any hidden variable, you will not be able to have certain level of correlation. So the experiment will show a low correlation. If the hidden variable do not exist, so quantum mechanics is a complete theory, is not a partial theory, we will see a correlation that is not possible by quantum concept. And there have been a lot of experiments done even in the 90s and even before. But there was always a critique, because as a part of the experiment, you have to take some random decision at the two sides of the experiment, right? The two detectors have to take some random decision. That's the key ingredient of the experiment. And we know that when we talk about random, what does it mean random, right? In software, you have pseudo-random generator. It's always a problem to generate random numbers. It's always a problem to generate totally not correlated random numbers. So this guy decided to do an incredible experiment. So to use as a random source two stars, two pulsars that are millions of years away from the Earth. So the photons that are coming from this pulsar are the source of entropy. And these photons have started the journey billions of years before we decided to do this experiment. So they cannot be, let's say, correlated with our experiment. And there are two different stars. So this has been called the cosmic experiment of the Bell inequality. And this experiment has demonstrated that, yes, the spooky action at distance happens. So there is no hidden variable. It's an incredible phenomenon. And on this phenomenon, there is organization and country that are building new generation of network. So this is the China network, but there is also London network, and more are coming. So this is to conclude, this is the Cisco vision, is to focus on building quantum network for different use case, connect different quantum computer, be able to exchange quantum states with quantum sensor, and enabling quantum data centers to have scale out of quantum computers together with the scale up that the quantum computer builder are performing. So with that, I just want to say that I'm dedicating this lecture to the memory of Professor Antonio Barone and his son Alberto Barone, who were expert in Josephson Junction and had the pleasure to be my mentor and my friend. And with that, thank you for today. I'm looking forward for the next session.
Thank you so much, Giuseppe. I have just stopped the YouTube stream. Thank you so much. Great presentation. Just a note